two companies, company 1 and 2, have just been founded, and we have a stock market crash occurring at a Poisson process distribution with rate lambda 0. Such crash would put companies out of business, and for j equal 1 and 2, so for company 1 and 2, there might be adverse events specifically tied to company 1 or 2. Whenever 1 happens or 2 happens, it doesn't affect the other company. And that event also occurs with the Poisson process with lambda 1 for company 1, lambda 2 for company 2. And then, if there has not been a stock market crash or adverse event of this type, then company J remains in business. We also given the information that these processes are independent of each other. Now we're letting x1 and x2 be random variables measuring how long company 1 and 2 stay in business, respectively. We are then asked to find the marginal distribution of x1 and x2. Okay, so let's start by writing down the distributions that we know and define what x1, x2 means. So we know that, let's call adverse event for company 1, that's C1. So it crashes whenever C1 happens, and that is a Poisson process. A Poisson process, we know, is equal to an exponential distribution. That's given in chapter 5 in Blitzstein's book, where we show that a Poisson distribution as the rate of events, basically the window where it can happen, becomes smaller and smaller so that it converges to a infinitely small window, so it becomes continuous. So exponential, then we write as we just given in this introduction. So this is for company 2, and then I'm going to define S being the stock market crash. It's also exponential. That occurs with lambda 0 rates. Now x1, so the duration of how long company 1 stays in business, that is equal to, what is that equal to? Well, it is equal to, it can stay in business as long as C1 doesn't occur or S doesn't occur, so the adverse event or the stock market crash. Whatever happens first will lead deterministically, with probability 1, to a crash of that company. So we can then understand that story as the minimum of C1 and S. And then that's the same thing for company 2. Minimum C2 S, like so. We are also given the information that C1 and S and C2 are all independent. So these are all independent, but X1 and X2 are not necessarily independent. In fact, they are not independent, because we know that if that a stock market crash occurred, it will lead to the demise of both company 1 and company 2. So there is information in some part of the joint distribution of where a crash happens. It will lead to the crash for both companies. Okay, so we're then asked to find the marginal probability. Let's do that for one of the companies. It will be totally analogous for the second company. So we can then define the CDF of C1 like so. These are just definitions of the CDF being the probability of x1 less than for event little x1, and that we just said was the same thing as the probability of the probability of, yeah, sorry, just lost my train of thought, the minimum of C1 and S being less than X1, like that. And then in order to get rid of this minimum, we can think about if we can reverse this inequality, we can think about whenever C and S are larger than X1, then we can write it like the following. So 1 minus P, so the complement of this is minimum of C1 S like that, and that now leads to the situation where either C or S has to be larger than little x1, and that is the same thing then opening up that minimum, writing C1, C1 larger than little x1, S larger than little x1. Okay, and now we also know that both those events are independent of each other. So that in fact is then 1 minus P C1, just going to well, let's just yeah, it's okay, S x1 like that, and then we know the distribution of these marginals, and they are in fact exponential. So we have exponential, and this is the complement, so this is only the exponential lambda 1 x1 minus C lambda 0 x1. Okay, and that could be written just as x1 minus lambda 1 plus lambda 0. So it means that the CDF of this x1 is basically distributed as exponential. You just write it down here on the side. So this whole thing here is exponential lambda x1 plus lambda lambda 0. Okay, that's the distribution of that variable, and then we can obviously take the PDF just by taking the derivative and get the PDF for that random variable. So that's the first part, and as I just said, it will be totally analogous calculating x2 here. We'll be just switching lambda 1 for lambda 2, and I see I made a little mistake here. This should be lambda 2 here, like so. Okay, let's move on to the second part. Here we are asked to find x1 being larger than little x1 and x2 being larger than little x2, and use that information to find the joint CDF. Okay, so this seems like a bit of a detour. Why calculate this? Why can we not just calculate the CDF immediately? Let's write it down and see why this information is helpful. And this has to do basically with the fact that we're taking the minimum of something. Okay, so here in this part, we are asked to start with calculating the probability of x1 larger than, just remove that little x1, those two events here, x2, and that, as we said, we can't open this up immediately because x2 and x1 are not independent necessarily. It's only these three events that are independent. So let's write out the definition of x1, x2, and that's the minimum of an adverse event happening, C1, to company 1 and the stock market crash. That's larger than x1. They have the minimum of adverse event for company 2 in the stock market crash. And that is larger than x2. Okay, and now we can write these minimums, just basically that's the same thing as C1 is larger than x1, S larger than x1, and the same thing here, x2 larger than x2, S larger than x2, like that. And we can rearrange things, so we can rearrange by seeing that Sx1 and Sx2 sort of belong to each other, and C2 and C1 are independent of each other and S. So that independence allows us to write the following. C2 larger than x2, and now we have S larger than x1, S larger than x2, like that. And we know the distribution of x1 and x2, and we know the distribution of this as well, and that's just by what we calculated earlier. And this is the same thing as the minimum of, now it's not at the random variable side, but at the value side. So what does this mean? It means that whatever happens first, x1 or x2, will fulfill the this condition that both these events will happen. Essentially, we're saying that whenever, if this is 1 year and this is 2 year, then a stock market crash happens, so this probability happens at then rate x1 and not x2. All right, that's fine. We now write down, this is then the complement of the exponential. So this is lambda minus exponential lambda minus lambda 1, it should be, sorry. X1 x2, that, and this is just minus lambda 0 minimum of x1 x2, like that. Okay, that's good. Now we have dealt with this first part here. Let's then go back to the question and see, okay, so that was interesting. We just calculated that. How is this helpful to find the joint CDF of these two random variables? Okay, let's write down what CDF means for x1, x2. That is the probability that x1 is less than little x1, x2 little x2. Okay, that's good. Now, what is this? What is this? Where does this lead us? Well, the problem here is that if we write out x1 and x2, we'll get the minimum here, right? Which is fine. But then in order to open up the minimum of two random variables, we need to switch the inequalities by taking the complement. And then we need to essentially open that minimum up, but that will lead to rather complicated situation. So what we do instead is that we take the complement of 1 minus, so it's basically taking this event and taking the complement of this event here. But there's one critical difference, and this is now that we need to, because we're taking the complement of two random variables, we need to then figure out what the all situations that doesn't fulfill this condition. And I've written or here, and this will seem a little convoluted. So what is really going on here? And let me just take a little detour now and show you how this is true. It took me a little while to figure fully out what is really going on. So let me put a little pin in here. We'll be continuing here, but I want to now explain why this is valid. Okay, let's do that by first drawing the support of this CDF here. Okay, let's draw the support and see what is going on. I'll draw here on the side. Okay, drawing here. What do we have? We have x1, the x1 event, and we have the x2 events here. All good. And then we're asked to look at the event where x1 is less than the little x1 and x2 is less than the event of little x2. Now, this could be anywhere, but let me just, let's assume it's here. So this is little x1. We'll start with the green. This is little x1. Okay, so x1 occurs here. Whoops, it was a little ugly. Like that. And then we have x2, perhaps being there. Okay, so what we are asked for to do is to find the area of interest, which is, I'm going to draw it in blue. So this full support area here is where this whole event is satisfied. Okay, so it goes all the way. Now this goes to infinity, but if you want to just add some constraints, you can think about it being basically a box here. And I think that's easier to think about, it being sort of a limited box, a limited support. We're taking the figuring out where the complement is. All right, good. So what does it mean to be well, let me do just one little thing here and makes it a little clearer. So if I write 1 minus the probability of, so we know that all, if you have an or, you add this event, the first event, the second event, like that. And then and then you subtract off the joint of those events. x1 x2. Okay, so what did we do there? Well, this is just the law, laws of probability when we're adding and subtracting. Well, we add two events, but we have added their overlap twice, so we're removing one of those overlaps. And this is in fact what will be happening in this little diagram here. So where is x1, random variable x1 being less than this event? Now I see one error I made here, which is that obviously we're taking the complement, so these inequalities should be pointing to the other direction. Okay, so let me change that. This is very important, obviously. Like the following, because we're taking the complement, so it should be pointing to this direction, like so. Okay, so let's think about where is this event, where is this event true? And we're looking now at the marginal of x1. So this is saying that little x1, the random variable, can be anywhere in this region here, right? Because that's where this condition is fulfilled. And this event, by the same token, can be anywhere in this region here. Okay? And so the complement of this event, I mean, this is what we are after, is subtracting this region and this rectangle here. Yeah, but what we've done if we subtract is that we have taken this part of the rectangle twice. One when we took x1 being larger, so this is one time, and then a second time where x2 was larger than little x2. So this is why we are subtracting off this region here. So this is why this event is equivalent to that event here. So just to clarify, so this is both the green and the orange area twice. Okay, I hope that makes sense here. Let me just move it a little so. So let's now continue. We've shown that essentially we've shown by this argument here that this OR condition is correct. Okay, now we're almost done. I think that was the trickiest part of this problem. So now this is just the probability of x1 larger than little x1 minus x2 larger than little x2. And now because we have a minus sign here, a minus sign there, we add them together. It's now a plus, sorry, so x1, little x1, x2 larger than x2. And now we see why we were asked, and this took a little depth into the argument to see why we were asked to calculate this expression, which is in fact this whole little thing here. And so that was just a way of saying that if you would, you know, just go by trying opening this up with the minimums, you'll be facing quite difficult calculations. So this is just another way of doing it smoother. Okay, and we know what the distribution of p x1 x2 is. P x2 larger than, let me just basically copy these guys in, so we know that this is that expression. Copy, just write it down here. We move this whole thing like that, and this we know as lambda, as we did from this expression here. Okay, let's see, we have this piece, it's the complement, copy it, paste it. Well, let's write out the simplified version. So it's x1 lambda x1 plus lambda 0, and it's the same thing for this probability here. So let's copy this. And here we have a plus sign, because we have a plus sign there. This is a minus. And now we are in the domain of the second company. So this is 2, 2, like that. And this is indeed the expression that we were asked to calculate for finding the joint CDF of x1, x2. And the main trick was, because we're dealing with a minimum, to take the complement in a disciplined way and really understanding the depth of what we're doing, or in terms of the support being counted twice.